Thank you for being here today. Today I'm going to share with you the open source development that I've been doing with the StarCraft II API from DeepMind. How many of you know the StarCraft II game? Okay, quite cool. Are you familiar with reinforcement learning and deep reinforcement learning? Yes? Okay, awesome. So I'm not going to explain the solution, the DeepMind or the AlphaStar solution. I'm going to go through the open source developments that I've been doing for the past 2 years, including the Blizzcon attendance experience. So feel free to reach me at the end with any questions you may have. Why is StarCraft II? StarCraft II is a real-time strategy game. It has like a setup from cooperative and competitive strategies, and there are like 3 main components that makes the game a huge and important and interesting challenge for machine learning. The first one might be like the elevated, a huge action space. We're talking about 10 elevated to 8 actions, which is like a huge scale jump from the typical benchmark for Atari games that have maybe 30, 40 or a few hundred. We're talking about huge scale jump. There is also a high level of complexity in the game regarding the macro and micro experience, as one of the things that you have to do is manage an economy and get build an army and then defeat your enemy. So there's kind of this high level strategic thinking of a type of game, and then it's a micro level. So it's interesting because it's kind of balancing in between those 2 things, and also it has a long-term sequential problems as the things that you do at the beginning of the game might affect the rest of the game. So environments. Why do machine learning, why is gaming built an environment as an environment for machine learning? So video games are great environments because they are systems that are safe for testing algorithms, at least, and you can use those algorithms later for adapt and test them in adapting in the real world. And then usually it provides a context for the real machine learning problem that you want to solve. So here in this case you have the 2 APIs. Today we're going to be digging into the PySC2, which is the API that DeepMind was building. So you can test a lot of algorithms. You can do multi-agents, you can do pure reinforcement learning, you can do multi-agent reinforcement learning. But today we're going to be talking about the DQN, okay? So the reinforcement learning paradigm talks about what is called the Markov decision process. I assume are you all familiar with that? Yes, more or less. So let me explain. We have an environment. There's going to be the StarCraft II setup, okay? And then we have the agent. The agent is going to be learned. The environment sends the states to the agent to see what is happening, and then the agent kind of learn a strategy with the policy, and then what it's doing is taking a decision, an action to the environment. So do this, build this. In this case, build a barrack or whatever, and then the environment is going to give a reward sign saying how well the agent is doing. When we talk about reinforcement learning, we have the value function, and then we have the action value function that kind of derives in the end with the Bellman equation. That is a Bellman equation is kind of saying how good is for an agent to be in a state and take a given action. So in this equation we have the reward, and then we have a discount factor with this Bellman equation in how it works in the future. So Reinforcement learning, like the core reinforcement learning, is like this equation, okay, the Bellman equation, and then we can use a lot of things to approximate this equation, right? In this case, what does deep reinforcement learning do? They use like deep neural networks for make like that approximation of the function. So how does this kind of cycle Markov decision process works in the API as such? So we have like the binary and the PISC2. The API sends a set of observation that is like divided in like several blocks that tells how the agent is going to process that information. In one hand, we have like the spatial features. There is like small like screens, kind of abstract screen. It's not a pixel to pixel information drawn to a convolution, but it's more like an abstraction of it. And then we have like also the non-spatial features that is telling things like how many gas do we have, how many gold do we have for building things. So it's more like standard tabular data for the game, right? So the idea that I want you to have from this is like the API is sending like kind of how the map is working, what is going on in the map, right? And some other kind of data that is like how the player is doing. So we have like the agent that's going to be the learner, and then the learner is sending like a response. In this case, can be like do a selection, build a supply, or move the units or wherever. So there's a problems of scale in this game, as like the full ladder games can like last 45 minutes, right? And if we are like passing through the API 45 minutes for all the frameworks, we actually do have like a lot of data, like spatial data to convolute and non-spatial data, okay? So what DeepMind did is like at the beginning, they released a series of mini games that were like bounded challenge of the games that they were tasting their agents how to solve it. For example, like we have like marines and we have roaches and then fight together. Or I have a base and I have like some units and then I have to start building an army. So those things kind of were like the first test bed of how to approach the full ladder game to solve like those problems of a scale. So, okay, so what is the agent? We have been looking at the Markov decision process. We have talked a little bit about the environment, right? We have seen the complexity of the environment, like that huge action space, sequential problem. And now we are going to be digging into the agent, which is like the learner, is like kind of the decision making. It's like the problem that is going to make the decisions. So what is the goal of the agent? The goal of the agent is to learn this policy, this control strategy that is going to maximize the cumulative or discounted reward, right? So what I want you to have in mind with this is like the agent is going to be learning things, and we are using a model, in this case doing with TensorFlow 2.0, a neural network, to approximate like this Bellman equation, that is the one that we have been talking before. So for that, the Bellman equation comes from the reinforcement learning world, and then we're using like deep neural networks to do that. So for this is more or less how the API works. So this is what the machine is seeing when you start the API. As you can see, like they don't see the marines or the units per se, but they see like kind of an abstraction of it. So that is like the map, the base, and like those blue cycles are the minerals, and then you have like the Seldons or whatever that they are moving. And then one of the cool things about the API is that they are able to kind of separate several layers that are going to be convoluted. So each layer is going to have like kind of information. So actually you can actually prune a lot of some of the layers that you don't want. You can take the information that you're interested in actually to process that image. Okay, so about this, This is like the architecture that was used for the mini games, like the first paper that was released. So with this, the idea is like they've taken like the minimap and the screen, like what are the spatial features that we have seen, but also the non-spatial features, and they make like a combination they call the state representation. And in the end, like they are like giving out the spatial action policy and the non-spatial action policy. So what does it mean? This means that like they take a neural network, they're going to, like a convolutional neural network, they're going to process all the kind of information that they consider spatial, and then they're taking also like non-spatial features, which are like the gas and the minerals, and they're going to bound it into that state representation. So as we have been talking before, the mini games are like those bounded challenges. And from now on, all the model that you are going to see, all the environments that I'm going to show you are from mini games. Just to repeat this key idea, the mini games came as there's like this huge sparsity when tackle the problem, and they build agents to tackle like specific problems. So here we have how one of the mini games work without training, right? So the mini game is like Marines against like an army of roaches, and then you can see that like the Marines are like doing random moves, right? They are not like, they are actually like losing like almost all time of the game. They are exploring like the map, they are not targeting like the position. So once the agent is trained, this is like the API, how the API is seeing what is going on. You can see like the difference, right? They are like, the Marines go all grouped and they go all for the roaches. So there's no random exploration around the space. So they go towards like that goal. There's one key thing that I want to tell you about like these mini games that is like highly related with the model, the neural network model architecture. Because like when we are approximating this development equation, we can use like several kind of different architectures. We can use convolutions, we can use like fully convolutional neural networks. So here we have like the benchmark of three kind of different neural networks. We have like the AtariNet best-mean, which is like kind of a industry benchmark. We have like a fully convolutional neural network, and we have like a fully convolutional neural network with memory, okay? And if you can see like how, I don't know if you can do this thing. Well, if you can see at the beginning, in the first, when they start to train, the fully convolutional neural network is giving the best results, right? Like the benchmark is about like 80 in the reward, and actually the AtariNet is giving like a totally like a good reward, and the fully convolutional neural network with memory is giving a really bad results. But in the end, in the long tail kind of training thing, the fully convolutional neural network with memory is the one who is giving best results. What does it mean? It's important to train the model in the long tail, okay? Because like at first, they might give you good results to say like, okay, I'm going to prune this model because it's like, at the beginning it's like working well, but until I don't have like that benchmark long tail kind of performance, I cannot take like that decision. Is that clear? Yes? So, well, I'm a huge fan of StarCraft. I've been playing since with my brother since I was a kid, and then by the time they released the API, they released like an opportunity to go to Blizzcon to do a workshop, and so to work on it and to do stuff. So I signed up. I went to Los Angeles, and then I'm going to show you what I was working for the application, how did I apply, and when I was working for that. So for this part comes more for the StarCraft fans, okay? So I'm a big fan of Protoss, okay? I've been like playing Protoss, like I think it's really it's complex, but it's like really powerful. It has like maybe more. Oh, sorry. It has maybe more macro management than micromanagement, because it's like really hard to manage the economy. And then I was thinking in which kind of unit I could work with, and precisely which kind of environment is going to make me build an interesting machine learning problem, okay? Because yes, this is about a video game, but it's about like getting an environment or getting like a setup that can be like an interesting machine learning problem that can be like, you can use it like in other kind of environment. So the central unit has like some special abilities that they are like the hallucination. They can produce units that are not really there, okay, with energy. They have the guardian seal that they can like actually help one army to be protected against the enemy, and the force field that can like actually get like a force field in between like two armies, okay? So the guardian seal and the force field has had that kind of impact in what we consider sword sequency problem, because we are talking about like the micro, we're going to the army management, okay? So it has like, it can like defeat the enemy as well, but the hallucination produce a unit that is not really there. And that can impact on how your adversary is developing their tech tree, okay, or their kind of the development of the macro strategy of the agent, of the opponent in this case. So what I'm trying to say here is that this unit, the sentry unit, has an impact in the micro and the macro, okay, part of the game, and it can like produce kind of it can like kind of try to cheat like the enemy to change its macro development. Besides, it can have like what we call like an impact in the long-term game. So this is like how the third iteration of the minigame that I presented to the workshop, in which we can see like the 4 aliens and a reaper against these four sentry units. The environment is called hallucinize, because like apparently like the sentries are like defending like an ice cave, and the goal of the agent here is to produce hallucinations to try to defeat the aliens. Why? Because the aliens are really good against sentries. If we make like that unbalanced kind of battle, we can actually force the agent to learn those special abilities, and we can produce like an agent that learns their special kind of abilities that they have. Okay. So is that okay? Everything is. We on the same page? Okay, so the key idea from this is like we are creating an environment which is like an unbalanced battle, so the agent can learn what we want it to learn. Okay, so okay, let's see. This is fun because like these are a little bit like some of the results that we were like studying. So this is what's happening like in a random agent. Okay. So the random agent was actually making the hallucinations using the special property, but like was like kind of this random exploration around the map again. Okay, it was not fire focus. So so yeah, like it was like using ability, but not pretty well. So here we have what we call like symbolic AI, scripted agent. So here it was working like pretty well. It was like producing like the structures that they want, and if you see like the icons are actually kind of defending, like in the first line of the combat with the sentries. And then when they won, they produced more sentries, so the sentries conquered the world. And it was like one of the benchmark that we were using. But we found some things. So we were using like this A3C agent, like a synchronous agent. And then we found like the agent decided that the optimal policy behavior was to do the hallucinations and hide. Okay? So this is what happens a lot, like in machine learning. We got like kind of a local optima, okay? And are we attaining our goal? Yes. Because like actually it's an optimal behavior, yes. Because like if the sentry is actually beat by the enemy, is going through the wall, through the goal. What I want to say here is like the behavior and the goal are not always correlated, okay? So it's important to design reward functions, to design policies, to design experiments that actually doesn't go exactly with the reward, but also with the behavior. What we can do is like kind of put those worlds together. So we have been talking about the agent again. Remember that the agent is like that learner, that decision maker is the one who is learning a policy, and then we have like the model neural network model that is going to help us to kind of approximate that Bellman equation, okay? And this model was kind of takes the representation of the environment. So today I have like bring how this would work in TensorFlow 2.0. So here like the thing it was like how if we take a convolution and we kind of put like the input like those feature layers that we have been studying and such. And then we kind of put a dense layer over it for what we consider the non-spatial features. And then we have like that LSTM last layer of memory. So we have like the model, but we have also like the policy. So here, like the policy, we used like Keras RL, that was like an API. And for here, what I wanted to tell you is like, okay, so here is basically a wrapper that transforms the policy into a linear, it's like a linear incremental solution. We have like the epsilon greedy policy, a kind of thing that it's like, it's a way of selecting random actions with uniform distributions from a set of those actions. And then here is like a DQN agent in which like the model we have built with TensorFlow 2.0. So yeah, you can do many things with the model. It's not only like those like, okay, you can build like a model, but then once you have built that model, you can optimize it, right? With the same model, you can do many things just to optimize that model. You can do, for example, you can do dropout, and you can like kind of unwind or put some cells to 0 to see how many cells of the layer are working properly. You can like, so TensorFlow has this random seed generator stuff. You can try many seeds because like maybe the seeds are working better, so the convergence is better. And then, well, you can like also like do hyperparameter tuning and try new models. So yeah, so I think that like I wanted to bring out this slide because I think that video games are great for building safe algorithms in safe environments, but in the end there's a huge field of application in between this. This is an open source project that I've been developing, but was like I was highly supported from BBPA. That was like the company I was working for at the time. And what we were tackling several problems. In that case, I was really interested in black swans. Does anyone know what a black swan is? Okay, so black swans, it comes from a mathematical book because it's are anomalies that have like huge impact over time. So when you see an event, it doesn't make like many sense, so it's an anomaly, but with the time you discover that it was like kind of highly the impact. So the central unit kind of like could have that, because like it was like producing like it was defeating the enemy, but it was also high level impact on the macro strategy of how the opponent was actually working. Well, I know this has like a huge conceptual load, okay? Because there are many concepts like nesting here. This is my GitHub name. There are like all the agents are there. I will post the TensorFlow 2.0 code briefly. There, up there, you have like a code lab that it's like available for you. So if you want to don't know anything about the API and want to actually get your first training agent, you can go there and you can go step by step. And yeah, and that was it. Thank you.
We'll go to the floor to ask some questions, but just for me, typical training times, how long will you...
Oh, that's a good question. So for the minigame for the Sentry, you can be training for a couple of days. Yeah.
In what specification?
Sorry?
In what specification? What computer specifications have you been training for 2 days?
Okay, so I've been working with the Google Cloud Platform, okay, with virtual machines, with from A16 CPUs.
Okay. So without CUDA?
Without CUDA, yes.
Okay.
Yes, I know that changed.
Yes.
Yes.
Okay, raise your hand if you have a question, and if you can let Gema know. Well, we're going straight back here. If you can let Gema know your name and where you're from.
Okay.
Hello, my name is Alexandros, and so I have 2 questions. So my first question is, when you spoke about bonding the spatial and the non-spatial features
Yes.
of creating a neural network, can you explain, if you go back to your slide, can you explain how is that possible in the final layer, or which way you are?
Yes. So
binding those two?
yes. So here, like as you can say, there are like 2 kind of like it's the input and the actions. Okay. So what the first thing that it's done is like the kind of the input that I consider like the special feature layers are put like in the convolutional layer, and then we kind of do a reshape of that, and then we make like the huge vector that is like 1 for 236, and then what we do is like in the memory we add like the action space, right? So we have like two kind of different data, okay? The input is going to be like the spatial, and the action is going to be like non-spatial. Yes, but I do really think that I should be more semantic with the spatial and non-spatial, so I will add it to the presentation.
Brilliant. And the second question is, when the agent found the local optima policy when it tried to hide, when you saw that the agent was trying to hide.
Yes.
Could you not reward negatively this action by putting a time negative reward according to the time? So at the moment then it passes.
Yeah.
If the time passes, then we would get
Yes.
Negative reward, then the agent would try to defeat the enemy as quick as possible.
Yeah. So here it's a really nice question. So the thing is like when we didn't put a negative reward, what we did is like if the time goes, the minigames episodes are timed, so you have like 1 minute or 2 minutes to solve it. So if you don't solve it, like the reward goes to 0. Okay. So one of the things of pruning is like kind of what we were thinking is like maybe we can give another kind of reward, okay, for the agent to stay, the sentries to stay near that. But like what you're saying is like adding negative reward. We tested at some point, and it didn't even find this behavior. So there was, what I'm trying to say is like setting up the reward to 0 when it ends the episode has been the best local optima behavior. It's not the best behavior, as you can see.
Okay, thank you very much.
Is another question there?
Yes, I'm from Barclays. So, my very quick question: how would you then perform surgery on any updates to the game?
Sorry?
How would you perform surgery? So, let's say, for instance, the sentry got nerfed, its attack went down by however many percentage decrease to whatever damage they do to the other units. But your algorithm has been trained so that the neural nets has been trained that it will do X amount of damage a second. So how would you then, I think the data, they call it performing surgery on an already learned neural network so that it takes the lessons from the past but adapts to the new update to the game.
Okay, so the question is how to measure the behavior in a more low-level thing.
So that you don't have to retrain the new algorithm to new sort of specifications. So you literally perform surgery to the neural net so that it trains new parameters, so to speak.
Yes. Yes. Okay. So I will tell you what we did. Okay. We took like so there were already several mini games released from DeepMind. What we did is what we trained on all the neural networks that like were there. Okay. And then we set up like a table with the rewards that they were getting. Okay, because at the end what we wanted is like the best model that could generalize across different mini games, right? So what we were doing is like we were taking AC3 and with the architecture that I was showing before, and we were trying in different mini games. So in the end, the surgery and kind of the analysis was based on this final reward. Okay, and also timing. Timing is super important. Okay, what happens if the same mini game we train like you have to get the goal in 2 minutes or 4 minutes. So I think I'm answering your question in terms of we benchmark with the algorithm that was working best on the 6 mini games that were already released, having into account like the cumulative reward over time. And then what we were really keen and interested in is like how is this generalizing well? So yeah, that was. If you have further, maybe we'll discuss later. Yeah, thanks.
Do you have any more questions? Yes.
Hi, thanks a lot. Really, really interesting talk.
Thank you.
So your discussion is related to these mini games and the approach to that seems really clever and sound. How would you adapt that in terms of memory utilization to, say, a full?
Okay, yeah. So there's a blog post and there's a full release paper by Nature about like full other games and how DeepMind has approached this challenge. Okay, where I could like to say about this, which is really really interesting, is that in the end, what worked from them was not like working with one single agent, but a multi-agent setup, right? So they were like training different agents that were actually losing and starting to compete in a game themselves, okay? But it's like highly complex. Why? Because like we are dealing with multi-agent, and then we're dealing with game theory. That is like how, which is like basic of economics. There are a lot of things about like game theory, but in the end it's cool as well because there are a huge metrics, right? And we can use also like deep neural networks for approximating like that function, so it makes sense. So the answer to your question for me is not as much as like that memory, who at the beginning I think they were trying that approach, but how in the end they get into another subfield of machine learning as multi-agent and game theory to solve like the full ladder game. So for me, the most exciting thing about the full ladder solution is like the leak, is how they put like agents to compete in the ranks, and they like beating and getting like the NASA equilibrium as the benchmark.
Do we have any other questions? No? Okay. Two great presentations tonight. I've really enjoyed this evening's TensorFlow. I hope you have as well. Kind of satisfied the video game nerd and the football geek in me. So I think let's give both our